In this video, I'm going to look at the derivatives of the inverse trig functions. So the first one here is inverse sine. Now you can actually look this up in the maths tables, and you'll find that it says that dy dx is equal to 1 over the square root of 1 minus x squared, with the caveat that x cannot be equal to plus or minus 1. Because then of course you'd get a 1 over 0 there, or 1 over square root of 0. But that's okay, because if you remember, the domain of our inverse sine function only went up to minus 1 up to plus 1. So this just means that it's not differentiable right at the ends of its domain, which we actually would expect. So x has to be greater than minus 1 and less than 1 for this function to be differentiable. But anyway, how do we get this formula is the question. So you can look it up in the table, but actually we have our definition for inverse sine, and we should be able to use that to derive this formula. So here's how we do that. First of all, we have y equals inverse sine of x. So let's turn that back into the sine function that we know, and say that the sine of y is equal to x. So y is inverse sine of x, sine y equals x. And now, like we've done lots of times already, we differentiate this implicitly with respect to x. So I'll just write it like this. Differentiate both sides with respect to x. So the derivative of sine y with respect to x, so by implicit differentiation, or by the chain rule, we differentiate with respect to what's in the brackets, and then we multiply by the derivative of what's in the bracket. So sine, we differentiate, becomes cosine. So we get cosine y, and then multiply by dy dx. And derivative of x is 1. So we just rearrange that slightly, and we get dy dx is equal to 1 over cosine of y. Now, that is actually 1 over the cosine of, we actually have y above, it's inverse sine of x. So we could leave it like that, but that's a really weird looking thing, and we actually already know from checking the table we should be aiming for this thing here, which is a much neater formula. So how do we get the cosine of the angle whose sine is x, which is what we have here? Look, inverse sine of x is the angle whose sine is x, and then we want the cosine of that angle. So we must do some trigonometry. And what I'll do, as I often do if I need to figure something out with sine and cosine, is I draw my unit circle. So this is a circle, radius 1. And in the unit circle, if you draw some radius here, and you make a right angle triangle, like this, if that's my angle in here, theta, now the length of that radius here is 1, because it's a circle of radius 1. So that blue line there, over 1, is the opposite over the adjacent, or it's the sine. So that's actually sine of theta here, that blue line. And the red part there is cosine. The length of that line is the cosine of theta. So from this, we can deduce by Pythagoras' theorem, we have a right angle triangle, cosine squared plus sine squared should equal to 1. So that's just Pythagoras' theorem. The square of the hypotenuse is the sum of the square of the other two sides. And actually that thing I've just written down is a formula that's in the book, in the maths tables. It's probably down like this: cosine squared a plus sine squared a is equal to 1 for any angle a. So we're going to use that formula now. So we have dy dx is 1 over cosine of y. But if we could write this in terms of sine of y, well, sine of y is just x. So then we'd have it in terms of x, and hopefully in a neater form than this ridiculous thing. So here's that formula applied to y. So cosine squared y plus sine squared y is 1. So I can say cosine squared y is equal to 1 minus sine squared y. Or I can say that the cosine of y is equal to the square root of 1 minus sine squared of y. Now, sine squared of y just means the sine of y squared. If you remember, the original problem was y is equal to inverse sine x, and we said x is equal to sine of y. So I can just pop this in here. So that cosine of y now is equal to the square root of 1 minus x squared. And now we can go and put that back into the formula we had before. So we got dy dx is equal to 1 over cosine of y. So we now know that that's just equal to 1 over the square root of 1 minus x squared. And that's the formula you'll find in the tables. So now let's look at how you do the same thing for cosine and tan. So here we have y is inverse cosine of x. So having seen the last one, try this one. Pause the video now and try this one yourself before I go through it. Okay, so same as before, cosine of y is equal to x. That's just the definition of the inverse cosine. Now I differentiate both sides with respect to x. So I differentiate cosine y, I get minus sine of y, and then times dy dx by the chain rule, or implicit differentiation. X becomes 1 when you differentiate, and so dy dx is equal to 1 over minus sine of y, or minus 1 over sine y. Now the formula we used before is that cosine squared of y, actually cosine squared of any angle here, plus sine squared of any angle is equal to 1. So it must apply to y. And so we're going to just rearrange this to get sine y in terms of cosine y, and hence in terms of x. So this time we'll say sine squared y is equal to 1 minus cosine squared y. Then we will take the square root of both sides, so that we have sine y is equal to the square root of 1 minus cosine squared y. I'll rewrite that now as cosine of y squared. That's just rewriting it. Now again, look back at this line. Cosine of y is just x. So that is equal to the square root of 1 minus x squared. And now I can substitute back in. dy dx is equal to minus 1 over the square root of 1 minus x squared. And that's it. It's just like the one for inverse sine. So the last one we'll do in this video will be inverse tan. So here's our inverse tan function. So again, pause the video and actually try this one before you look at the answer. You should have everything you need. So like before, y is inverse tan of x. So the tan of y is equal to x. Again, I will differentiate both sides with respect to x. The derivative of tan is secant squared. So here we go, secant squared of y, and then times dy dx is equal to 1. Now secant, if you haven't seen it before, is just 1 over cosine. So that's just 1 over cosine squared, but I'll use secant here. There's the definition of secant, 1 over cosine squared. I'll use secant there because we're going to use an identity involving secant in a second. So I'll solve this like I did before first, to get dy dx is equal to 1 over secant squared of y. Now you'll notice that's just cosine squared of y, but we'll need that secant now in a second. This time I'm going to go back to my x equals tan y, and I'm going to work from there to figure out what that 1 over secant squared is. So x is tan y, x squared is tan of y squared. 1 plus x squared is 1 plus tan squared of y. So 1 plus x squared is equal to secant squared of y. Now that's why I left my secant in there, because there is this trig identity that secant is just 1 plus tan squared of y. So you can find that in the log tables. If you draw out your unit circle, you may be able to prove that for yourself, that 1 over tan squared is equal to cosine squared, based on that right angle triangle that you draw. But I'll take it for granted here for now, that 1 plus tan squared y is secant squared, and then we're almost done. Secant squared y is 1 plus x squared, and so my dy dx now is just equal to 1 over 1 plus x squared, and that's the formula you'll find in your log tables, but that's how you get it. So that's the derivatives of the inverse, sine, cosine and tan function.